Hey everybody, it's Mr. Oliver again. This is going to be the solution for the AP Physics C Unit 5 review questions, and this is going to be for free response question number 2. Let's get to it. Alright, so this question is a little bit confusing on the setup initially, but I think once you understand what's happening, it's not too terribly confusing. So what we have here is a top-down view of a disk that's rotating around. Okay, so this entire platform is going to be rotating. And attached to the center of the disk is a small, slender rod of length D. All right, so you can imagine you got this disk, and there's like a tiny little rod in the middle that's a length D. And attached to the end of the rod is a little spring. All right, so if I were to kind of sketch that out, let's see if I can just sketch that out. Here's the rod by itself, and we've attached a spring to it, and then on the end of that spring there's a mass. Okay, so you can imagine this little setup is almost like a pencil with a spring on top of it and a little block on the end of that spring, and it's attached to the disk, so the entire thing's spinning like this around that central axis. Okay, now it goes on to tell that the mass is free to move, there's no friction, it's constrained to be going along this slot. So the only motion on this thing that can move is in or out away from the radius. Okay. It says the equilibrium length of the spring is d over 2. So right now, in this figure 1, it is at a relaxed state. It's at an equilibrium position. It tells us information about the block, the rod, and the platform. The block has a mass of m. The rod has a mass of 3m. Okay, so here's a mass of m. The rod has got a mass of 3m. Okay, this is the block. That's the rod. And then the table, the platform that it's sitting on, the entire circle, this whole thing is a mass of 5m. All right. It also tells us what the rotational inertia of the rod is. It's md squared over 3, or 1/3 mr squared, if you want to call it that. 1/3 mr squared. And then for the platform, it's 1/2 mr squared. Right. I like to do this sometimes when I see a lot of weird variables and subscripts and stuff. I try to make it simple so I kind of understand what's happening. So it says the motor begins to slowly rotate the platform, and so it starts speeding up faster and faster and faster until it reaches a constant speed. And so this thing, when it's reached its maximum speed, we're in figure 2. And what's happened is that spring has stretched an additional d over 2. So originally it was this long, and then it stretched this long. All right. So if you wanted to call it in terms of like a spring force, this would be your x value. When we're talking about spring force is minus kx, that's the x. Okay. Answer the following questions for the platform rotating at constant angular speed. So we're talking about in this scenario, figure 2. Express all your algebraic answers in terms of your mass, m, your distance, d, omega, which is the speed, and physical constants, which would be like g or whatever. So for the first question, it asks, derive an expression for the spring constant. Okay, so to calculate spring constant, I'm going to use the spring force equation, but I'm also going to think about it in terms of overall. F equals ma is never wrong. It's never not going to work. So in this case, what force am I talking about? Well, that's the spring force. That's kx, right? And then the acceleration has a specific type of acceleration. Because that thing is going to be going in a circle, the centripetal force is what's causing this block to stretch out. In other words, the inertia wants to stretch out. And so the spring force is actually the centripetal force. It's what's keeping it from just flying away. So this is v squared over r. Or if you like it better, because we're talking about omega, you could also say it's m omega squared times r. So this is what I've got. I've got kx is equal to m omega squared times the radius. If you remember, from the problem statement, it said that x was d over 2. That's how far it stretched. So I'm going to make that substitution in for x, And then all I need to do is solve for the variable k. So I'll have k times d over 2 is equal to m omega squared times r. Now r is how far away the mass is from the center. So in this case, my r value is going to be all the way out here. This is going to be my r from the center to the edge. Well, that's the radius, which is just 2 times d. So my r value is 2d in this case. 2d. All right. So as you can see, the d term is going to cancel. I'm going to multiply by 2, and this is going to turn into 4. And so therefore, my spring constant is 4m omega squared. That's an expression for the spring constant. All right. That was worth 3 points, by the way. Or no, not 3 points, my bad. That was worth, yeah, it was 3 points, plus 3. All right, question B, the first part, says determine expression for the rotational inertia of the block around the axis of the platform. Well, that's pretty simple. If you have any kind of an object at an extended distance and you're treating it as a single point mass, such as a ball on a string or a satellite going around a planet or something like that, and it has a mass at a radius of r, the rotational inertia is just m r squared. All right. So in this case, the radius r is the distance away from the center. So once again, that's 2 times d. So for the block, we've got the mass of the block, which is a single m, times 2d squared. So in the terms of the variables that they're giving us, it's going to be 4md squared. That's the solution. That's worth 1 point. For part C, or the second part, this is for BI. BII, it says derive an expression for the rotational inertia of the entire system. So for the entire system, total system inertia, it's going to be for the block, which we just determined, plus the platform, plus the rod. Yeah, can't forget about the rod. Okay, so the rotational inertia of the block is 4md squared. For the platform, it is 1/2 mr squared, but the m in this case is 5m, that's the mass of the platform, times the radius of the platform, well, that's 2d. So 2d squared. And then for the rod, it's 1/3 m of the rod, which I guess was 3m. So 3m times the length of the rod, which was d squared. Sorry, I was off the page there. Okay, so we've got rotational inertia of the block, 4md squared. Rotational inertia of the platform, which is 1/2 mr squared. M is 5m for the platform. R for the platform is 2 times the distance d. And for the rod, it's 1/3 the mass of the rod, which is 3m times d squared. And so when you reduce all this down, combine like terms, you end up getting, for the system, the rotational inertia is 15 md squared. That's the total system inertia. And I believe that was worth 2 points. Yeah, plus 2. All right. So for part C, it says to determine an expression for the angular momentum of the entire system about the axis platform. That's pretty easy. Angular momentum is just our variable L, which is the rotational inertia of the system times the angular speed of the system. So that's just going to be 15 md squared omega. That's worth 1 point. Okay. For part D, we've got a new scenario. It says, while the system continues to rotate, a small mechanism in the pivot, which is right here, moves the rod slowly until the center of the rod is positioned on the axis, as shown below, or shown above. The same constant angular speed is maintained. So what's happening is there's some kind of device in here that's pulling the rod closer towards the center. Because remember, if this was the rod right here, it was on the end. But now what's happened is there's some kind of device that's allowed that rod to move to there while maintaining the same speed. And we want to derive an expression for the distance x that the spring is stretched when the rod reaches the new position. Okay, so for part D, we need to set this up using the spring force again, just like we did in the very first part. So I'm going to use F equals ma once again. My force is the spring force, kx. My acceleration is a centripetal acceleration, so m r omega squared. All right. Now this time I know what k is. The k, the spring, hasn't changed. That's 4m omega squared from previously. X is our variable. That equals m. And I'm going to leave omega squared up front. But the thing I don't know is what is my new r. Okay. Well, in this case, it's the distance from the pivot to where that spring is. So if you look at this new diagram, my r value is from here to my mass, because that's the thing that is being centripetally accelerated. So if that's true, then this rod, which was originally distance d, is now a d over 2 to the bottom of the spring, plus a d over 2 plus x. So in other words, d over 2 plus d over 2 is just d plus an extra x. All right. So this now my new radius here is d plus x. All right. And so it takes a little bit of algebra, but it's not too bad. Solving for x, we can get rid of the m, which is nice. The omega squared actually goes away, and so what we're left with is 4x is equal to d plus x. So that means that 3x, I'm moving this over here, subtracting by 1, 3x is equal to d, but we're solving for x, so x is d over 3. So it's stretched a third of the original d distance. Oops. All right. Part D was worth plus 3. All right, part E, lots of parts on this one. Oops, wrong one. Part E says, is the angular momentum of the entire system increasing, decreasing, or staying the same? So what you need to think about is what is angular momentum? Well, angular momentum, which is L, is equal to I omega. All right, so from the problem statement, it says omega stays the same. We're keeping the same angular speed. So this term is just a constant. So then we got to say, well, does I change? Well, as that rod moves in, originally it was kind of like this, but then the rod moved like this. So if you think about if you go back and look at your table of rotational inertias, this has an equation I is equal to 1/3 ml squared, whereas this has an equation 1/12 ml squared. So by moving it into this little halfway point, you reduce the rotational inertia of the rod by 4 times. Okay, so that means that the entire system angular momentum had to decrease as well. So I decreased for the system. So for the question E, does the rotational or does the angular momentum decrease? You'd have to say yes. Sorry, not angular momentum. L decreased. All right. As that rod moved in, the rotational inertia of the rod decreased. Therefore, the angular momentum of the system had to decrease. F says, in order to keep the system rotating with constant angular speed, is the motor doing positive work, negative work, or no work on the rotating system. Well, what is work? Work is an energy term, right? But specifically, work changes energy. You always need to think about that. That's what work is doing. So you got to ask your question, is the system changing energy? Well, what kind of energy would you have? Well, you'd have kinetic energy. So you need to ask, does the work change the kinetic energy? Well, how do I calculate rotational kinetic energy? Well, K is equal to 1/2 I omega squared. Well, once again, because this omega stays constant, I can't consider that. But we just previously said that the rotational inertia does decrease. And so that means that the work caused the kinetic energy to decrease, right? The kinetic energy decrease. So that means that yes, the motor did negative work in order to decrease K rotational. This should be rotational, right? So the work is a negative work. You're decreasing the overall energy. All right, and then the last part says, on the block and figure below, draw a single vector representing the direction of the acceleration of the block. Okay, so here's what we need to do is we need to find out what kind of accelerations we have. Well, first of all, this is going in a circle, so there is a centripetal acceleration that points inwards towards the center. There is definitely some kind of acceleration pointing down. That's a centripetal acceleration. But what about the tangential acceleration? Well, we have previously said that the kinetic energy was decreasing, correct? So that means that there had to be some kind of a work term, some kind of a force to cause kinetic energy to decrease. Well, that would be a torque, right? It's not immediately obvious, but there was some kind of a torque on the system to cause that spring block disc system to lose some kinetic energy. Even though the speed stays same, there had to be some kind of a torque. Well, a torque going in the clockwise direction would create that. And that would cause there to be some sort of acceleration in the opposite direction on the block. Not necessarily the whole system, but on the block. So there is a tangential acceleration created by a torque causing there to lose kinetic energy. All right, so the combination of these two accelerations would result in a net acceleration going down and to the right. That would be the net acceleration on the system, or on the block. For the system, it would be zero because the angular speed is constant. But for the block, yeah, it is accelerating down and to the right. All right, guys, that was a tricky question that came from a few years ago, 2014, something like that. So it's on College Board's website if you want to go check out some of the comments and things, that commentary that they made on it. But anyway, that's the end of this solution. If you have a question, please let me know, and we'll talk to you on the next one. Bye.